Okay, so we'll go over this tutorial. I thought I had a recording of it. I even thought I had annotated version, but I don't. So anyway, so we start off with this Gauss's law, capital Phi, and well, it's not quite Gauss's law. This is expression for flux. So in basically E dot A, although it's usually expressed in its differential form, dA, because as we looked at last week, you can divide any complicated surface into little surfaces because we want to satisfy we want to use this pseudo vector, the A vector, and so it presumes a flat surface, or at least a almost flat surface, so it's easy to calculate the area. So and now we're talking about closed surfaces, so that means that the flux lines, give me a minute, yeah, flux lines pointed out of an area, so any Gaussian surface, if you have an A and any E vector, E flux line, in this case, this is positive, so the A vector, yeah, that's right, now I got it. A vector always points out. Remember before it was arbitrary. I'm going to just finish eating my lunch, so I'm a little food coma here. Okay. So then if the flux line is parallel, it's positive, or at least it's a acute angle. If it's greater than 90 degrees, it's negative. Okay, so, and then one thing to notice that it doesn't come out to be flux lines per area. It's E field lines times, or E vectors, times and dotted with area vector. So as the magnitude of the E vector goes down, the area will go up. And that's why we can make a statement that the flux is constant, no matter what size we make the area, within reason, because if you make a different size, then it changes the amount of charge inside. But just if we imagine some point charge all by itself, we can keep making the Gaussian surface bigger and bigger, but the flux stays the same. Okay, so let's see what we got here. So we see that the flux lines come into C, so any flux going into C is going to be less than 0. Flux lines leaving are going to be greater than 0, and flux lines that they don't even cross, they're at 90 degrees, so that's 0. Now, sign and magnitude, well, it's just a question of counting. And some people got 7, I got 5. So let's see, so the sign and magnitude of the flux. So Gauss, it's hard to say, right? I'm just going to give it an arbitrary number of 5. And then this one, since it's the same number come in and the same number come out, that's negative 5. So the total flux is 0. Okay, so here the lines cross all the surfaces, and they only go in, right? You don't see any line going out. So this is this is less than 0, and it said just find the sign, so that's easy. We don't even need the magnitude, because if they're all negative, then the sum has to be negative. Okay, now here we have lines going out and lines going in. Now, since they're both the same magnitude, we know that they're going to have this star kind of pattern of flux lines, and they're going to be identical, and the only difference is the way an arrow points. So that's for positive, and then the negative charge would be negative, right? So I'm going to say, by looking at this, that surface A is going to have, since it's fixed area, but it's further away from Q0, it's going to have more positive lines, so that's going to be greater than 0. Surface B is going to be 0 because any lines that pass in or out are pretty much going to be matched. And then surface C is going to be pretty much less than 0. But because of this symmetry argument, and this is also a case of we can make the cylinder bigger, it wouldn't matter. Since all the flux lines of plus Q sub 0 will be canceled by all the flux lines of negative, we're going to call that 0. Now here the flux lines go out, and so it looks like, and they're all going to go into A, so that all the ones into A, so that's going to be less than 0 because the A vector is going to point out. Surface B, it looks like they're also all going to be 0, huh? I mean negative. No, positive. They're all going to point out. And same thing with surface C. But we see that no matter what, every line that enters leaves. So every line entering also leaves. So if that happens, that means that the next flux is 0, and it's said to explain. The other ones didn't say explain. Check your results. All right, we've been through that. Okay, now let's take a look up here. So it says here, the Q enclosed over epsilon 0, is it consistent, right? Yes, because all surfaces, I suppose, all shapes, but with which had no charge or canceling charge at flux equal to 0, and then net charge inside equals flux not equal to 0. And plus Q is plus phi, and minus Q is minus flux, negative flux, if there's a net. Okay. Part D of section 1, try to determine the sign of the, try? Okay, you tried. The net flux is 0, because once again, every line that enters also leaves. So they're all going to enter into A. Some are going to exit through C, some and B, etc. But all that enter leave. So that means that the net flux equals flux A plus flux B plus flux C equals 0. So that means that if I add together A and B, I get negative 8 Newton meters squared per coulomb. So that means that this implies that flux B equals plus 8 Newton meters squared per coulomb. Okay, find the net flux. Okay, so once again, it's 0. Does it say explain? No. But that's just because every flux line that leaves, enters, leaves, and then these go the opposite direction, but every flux that enters, leaves. Here it's plus net flux, so it's plus Q0 over epsilon 0, because 4 of the minus Q's will cancel 4 of the plus Q's, so I'm left with 1 positive Q. Then here, this is plus Q's 0 over epsilon 0, because every flux line from the minus 1 will enter and leave. And this one also is plus Q0 over epsilon 0, because even though this is huge, every flux line that enters is going to leave. Okay, 3 spherical Gaussian surfaces to the right. In case C, there's another one there. Okay, so remember, the number of flux lines you see and the surface area, so the number of flux lines kind of stays the same, the area gets bigger, right? But you got to remember it's the E vector, not the, even though we use the flux line, that's just a framework of thought. We have the field vectors, so you have a field vector of a certain strength here, you're going to have a field vector of a smaller strength here, but the surface area is going to be bigger. So if E goes down, A goes up, vice versa. Here, case A and C are going to have the same flux. The trippy thing is here, though, that it's not going to get you the electric field at a point here. It gets you the electric field of the charge that's enclosed. So Gauss's law doesn't really help us much here. Yeah, so they all have the same charge. We've established that we believe this. So if we believe this, then student 1 has to be right. Okay, so this is part of my explanation. We believe from earlier, so we built up to this part. The page 1 and the top of page 2, we built up to this. We accept this, so that statement has to be true. Let's see, electric field in case B is weaker than case A. Yeah, but the surface is bigger. And electric field strength, yeah, well, that's contradictory. It's proportional electric field strength and area, not just electric field strength. So that's nothing, that's no good. I was A and C, the charge. No, you see the minus 6Q, all flux lines from that will enter and leave. So the flux is not different. So that's because the minus 6Q lines all enter and leave. And this is because it's proportional to E and A, not just A. E, not just E. Okay. All right. So indicate location of the charge key. Location is here because that's where the charges are. And this is, we're assuming this is a right cylinder. So that means it's, it is constant radius, and that the axis cylinder and the axis is perpendicular to the ends. That's what a right cylinder is. Axis perpendicular to ends. And what else? Whatchamacallit? The cross section area is constant. That means it's not tapered. Okay, that's the definition of a right cylinder. So we can pick A1 or A2 because that's one. It's the enclosed charge is just here. What is the net charge enclosed? Okay, so sigma is defined as Q per area. So Q then is going to equal to sigma times, and in this case, sigma 0 times A1, or it could equal sigma 0 times A2. Sketch the electric field lines. So the field lines point out, point away, like that. Does the Gaussian cylinder affect the charge distribution? No. The cylinder is imaginary. So by definition, it can't affect it. Okay, you got E, L, E, R. How many magnitude? They're going to be equal to each other. Because we calculate. Didn't we calculate this before? But anyways, because there's a single sigma sub 0, and so the sheets have to. Doesn't matter what side you're on. Magnitudes, I suppose, if you want to get picky. And there's symmetry, and there's no R dependence, so it doesn't matter how far away we are. I don't know if we're allowed to say that. But by symmetry, if I stand here or I stand there, it looks the same. How do the magnitudes of the areas areas? Oh, well, it's a right cylinder by definition. It looks that way, and we're going to declare it. So that means that A1 equals A2. To which surfaces is there a net flux? Well, it's A1 and A2. Because if I make A3 is always as a vector. I don't know if that's a good word. There's no. If you say any dA3, I suppose, is always perpendicular to E. So that means that the cosine of angle is equal to 0. Cosine of 90. What am I doing? Cosine of 90 equals 0. Okay, explain using a sketch to the... Oh, okay, right. So, well, the field lines, they're all over the place, right? They not just inside, but you see that they're parallel to the surface or perpendicular to the A vector. And then similarly over here. Okay, write expression for the net in terms of the okay, so flux net equals E left A2 plus E right A1. I want to simplify it, so A1 equals A2, E left equals E right, so the flux equals 2 times E right A1. Which one? Usually find the magnitude of the electric field at the right end. Okay. Let's see now. It equals, right, so we have 2 ER, A1 equals Q enclosed over epsilon 0 equals sigma 0 A1. Yep. So the A1s cancel. So we're left with ER equals sigma 0 over 2 epsilon 0, which we saw that last week. And what is the electric field? It's the same as we've already established. Oh boy. Notice that it's independent of the area. Just depends on the charge per unit area. Use the electric field in the leader should depend on the distance from the sheet. Oh no, no R dependence. No, there's no position dependence even, so no matter where I am. With the electric, yeah, right, because I drew them so that they're all evenly spaced. Equals constant field. Constant mag and direction. So it doesn't matter where you are. No position dependence. Okay, find the net charge enclosed by the gallon. So there's 2 of them. And then, so that means there's 3 sigma 0 times A1. And that is, yeah, that's the total enclosed. Okay. EL, the magnetic electric. It's EL, okay, so if left and right end caps, so that means that we're talking about this is E right and this is E left. So we're going to ignore in between. So just even now, ER equal to EL, magnitude anyway. And we see that don't forget the A vector is pointed like this. This A vector is pointed like that. So they're always parallel to the E vector. I mean, A vector and E vector. Yeah, A vector and E vector. The flux lines and the vector, yeah. Find the net flux to the Gaussian. Oh, yeah, right. So this is similar to earlier. Where now, let's think about this. We have 3 sigma 0 A2 E left plus 3 sigma 0 A1 E right. So that ends us up with, since, again, A1 equals A2, E right equals E right left, and both mag and direction. So in fact, we can express them as vectors. So that means that 6 sigma 0 A1 E right equals I'm doing something wrong. Wait a minute. Yeah, there's no sigmas in here. So that disappears, and this is just 2 again. That disappears, and now equals to 3 sigma 0 A1, that's the charge enclosed over epsilon 0. So once again, the A vectors cancel out. So E right equals 3 over 2 epsilon 0. So it's 3 times stronger, which is what we would expect. Superposition, yes, because as long as I'm not in between, I have, if we call this 1 and 2, field 1 is, let's see, 3 sigma 0. Field 1 is sigma 0 over epsilon 0. And then the other one is 2 sigma 0 over epsilon 0. And we know that they both point in the same direction, so we add them together. All right. Explain. Outside, find the field distance L0 to the right of the rightmost sheet. Oh, yeah, I did that, but it has no position. So outside of the 2 sheets, and so we know this is the field of number 1, number 2, and E1 and E2, both, they're in the same direction. And so if that's true, then and there's no position dependence, so we can add them together. And it's then we end up with exactly, okay, what did I do wrong? Oh yeah, 2 and 2. Yep, they're the same. Okay, So stop this, get it up